As you recall, when a double napped cone is sliced by a plane, we get three types of non-degenerate conic sections called the ellipse, the parabola, and the hyperbola. We have previously discussed the ellipse and parabola in other videos. In this video, we're going to study the hyperbola. Remember that if the slicing angle is somewhere between 0 and the vertex angle, meaning it's basically less than the vertex angle, the slicing happens to cut through both naps of the double napped cone. Whereas with the other ones that we have studied so far, only one nap of the cone is sliced. And this slicing creates this interesting figure at the intersection or at the cross section, which we call the hyperbola. Formally speaking, a hyperbola is the set of all points in a plane such that the absolute value of the difference of the distances from two fixed points is constant. The two fixed points are called the foci or focuses of the hyperbola. So, whereas in the definition of an ellipse, we wanted the sum of the distances from any point on the ellipse to the two focuses to be constant. In this case, we want the absolute value of the difference between those distances to be constant. And it's this requirement of the difference of the two distances is what basically kind of takes an ellipse and rips it apart into two parts. You can think of it that way. So think of the plus kind of joining the ellipse and the minus causing the basically separation into two pieces of this figure that we call the hyperbola. Here we have a hyperbola that is centered at 0, 0, and we call this segment joining the two vertices here the transverse axis. So this hyperbola would have a horizontal transverse axis, and the vertices are at A0 and negative A0, and the foci are at C0 and negative C0. So we know from the definition that if we take the point P here, which is on this hyperbola, the absolute value of the difference of these two distances is going to be a constant. Now, that means, given that the vertex V here is also one of the points on the hyperbola, it should also satisfy that requirement, meaning the distance between, well, the absolute value of the distance between V and the far focus F prime and V and the near focus F should also be a constant. Now we can find that distance very easily, and we don't need to use absolute values because of the positioning. We can see that the distance between V and F prime is going to be larger than the distance between V and F, so therefore we'll end up with a positive quantity anyway. So what is the distance between V and F prime? Well, if you think about it, this distance here is A right here, right? And this distance here is C, right? We're talking about the positive distance. So, but if we can just subtract in this manner, say A minus, what's the coordinate here? Negative C, then we'll end up with the same result, which is A plus C, right? So remember, whenever you want to find the distance between two real numbers, you can just take the larger one and subtract from it the smaller one. So we take the A here, which is larger, and subtract from it negative C, and we end up with A minus negative C. Now, minus the distance between V and F. So remember, in this case, C here is the larger number and a is the smaller number. So that distance there is going to be c minus a, right? So we get a plus c minus c, and then distribute the minus, so plus a. The c's cancel out, and we get 2a. So that fixed difference that we're looking for in the sense of for any point and the distance from that point to the two foci and the absolute value of the difference of those two distances should always end up being what? 2a. That's a number that we're going to need to use to further develop the concept of a hyperbola. So we know that the constant in the definition that we've discussed on the last screen between any point and the two foci and the absolute value of the distance from those points should be 2a for any point on the hyperbola. So if we now define b in this way, let b be the square root of c squared minus a squared, then we end up with this relationship: b squared equals c squared minus a squared, and therefore a squared plus b squared equals c squared. Now, all three of these numbers are going to play a significant role for us as we proceed. So we now have enough information so that we can drive the equation for a hyperbola centered at 0, 0 with a horizontal transverse axis. The development is going to be very similar to what we did to find the equation for an ellipse. Here we can of course position the point on the hyperbola for our analysis so that one of the distances is clearly going to be larger than the other one, so that we can, when we want to handle the difference, we don't have to get absolute values involved, which would unnecessarily complicate our calculations. So let's go ahead and look at this point on this hyperbola. We know that the absolute value of the difference between these two distances should be 2a from what we just discussed in our previous screen. So the distance between p and f prime minus the distance from p to f, which is the closer focus here, should equal to the constant we came up with, which was 2a. Now, that's basically 2 times the distance from the center to either vertex, right? So basically applying the distance formula again, like we did in our video for ellipses, we get the distance between p and f prime, we get x minus negative c, right? And then we have to square that, plus y minus 0, and then we have to square that, minus the square root of, now we deal with the distance between p and f, the closer focus, and we get quantity x minus c squared plus quantity y minus 0 squared, just applying the distance formula. And we clean that up, we end up with the square root of quantity x plus c squared plus y squared, because y minus 0 is just y, minus the square root of quantity x minus c squared plus y squared equals 2a. Just as we did previously, we're going to go ahead and take one of these radicals to the other side so that it's easier to do algebra when you have no more than one radical per side. So we end up with this equation. Now we go ahead and square both sides. When you square the left side, of course, that's just a simple radical expression. So when you square that, you basically just get the radicand, which is the expression under the radical. So we get equals. Now we're going to have to square this two-termed expression. So let's go ahead and expand x plus c squared. So we get x squared plus 2cx plus c squared, and we already have a y squared. We don't want to forget that. On this side, remember, you get the first one squared, which is just going to be 4a squared plus 2 times the first times the second, so we get 4a times radical quantity x minus c squared plus y squared, plus you have to square the second expression here, and that's a radical expression, so when you square it you just get the radicand. Okay, continuing our work and simplification here, and again, you should be able to do this on your own, especially since you saw me do this for the ellipse. I would strongly recommend pausing the video and doing that, and then coming back to make sure you did it correctly. So we get 4a squared plus 4a times the square root of that expression minus, here we're just working out what the quantity x minus c squared is, which is x squared minus 2cx plus c squared plus y squared. We have the y squared, of course, already there. So now notice there are many cancellations, right? The x squared cancels the x squared here, and the c squared cancels out, the y squares cancel out, right? So we basically have 2cx on the left side. On the right side we have 4a squared plus this expression, 4a radical quantity x minus c squared plus y squared, and then minus 2cx because everything else cancels out, right? So now if I just move this to the other side, we end up with 4cx equals minus 4a squared equals 4a radical that expression, and then notice there's a common factor of 4. We can divide it off, so we just get cx minus a squared equals a radical quantity x minus c squared plus y squared. Now we only have one radical left. We can go ahead and square both sides again. So we get the square of this expression, cx minus a squared equals a squared, because we've already squared the a, and then times the square of that radical. So now we apply the square of a two-term expression again. We get c squared x squared minus 2 times a squared times cx plus a to the 4 equals a squared times, remember when you square that you just get the radicand, and we go ahead and expand the x minus c squared. We get x squared minus 2cx plus c squared, and then plus y squared. All right, so just continuing our process here, we get c squared x squared minus 2a squared cx plus a to the 4 equals, here we're just distributing the a squared, right, by each of those terms, and we end up with this expression. Now we notice that there is some simplification that's possible. So we get a to the 4 plus c squared x squared. We cancel out those two terms because they're the exact same term on both sides of an equation. They can be canceled. And on the other side, we get a squared x squared plus a squared c squared plus a squared y squared. All right, so now we'll bring these two terms that have x squares in them together. On the left side, we get c squared x squared minus a squared x squared minus a squared y squared, because we're bringing the negative a squared y squared as well. And on this side, we're left with a squared c squared, and we bring the a to the 4 from the left side to the right side, so it becomes minus a to the 4. Now if we factor out an x squared from these two terms, we get x squared times c squared minus a squared minus a squared y squared equals a squared times c squared minus a squared. If you remember, c squared minus a squared is b squared. Let me show you from the previous screen for a second. See, we defined b to be the square root of c squared minus a squared, so that b squared becomes c squared minus a squared. That's the substitution we're making. So we're replacing both of these c squared minus a squareds with b squared. So we get x squared b squared minus a squared y squared equals a squared b squared. So now we go ahead and divide both sides by a squared b squared like we did previously with the ellipse, so we can end up with a 1 on this side. On this other side, we end up with x squared over a squared because these b squares would cancel out, minus uh, y squared over b squared because the a squares cancel out next, and we end up with this nice simple formula for a hyperbola with a center at 0, 0 and with a horizontal transverse axis with vertices at a0 and negative a0 and focuses at c0 and negative c0. All right, so extremely similar to the equation for the ellipse, except instead of a plus, as was the case with the ellipse, we have a what? Minus here. At this point in your mathematical progress, you should be able to do a derivation like this without a great deal of difficulty. So if it doesn't happen the first time, try it again and again and again until it does, because that's how you gain mathematical strength. All right, let's go on. All right, notice that we can quickly locate the x-intercepts of a parabola with center at 0, 0 and a horizontal transverse axis by simply setting y equal to 0 and then solving for x, right? So we get x squared over a squared minus 0 squared over b squared equals 1. That's, of course, just going to be 0. So you get x squared equals a squared. So we get x equals plus or minus a. So the x-intercepts are at a0 and negative a0, which actually happens to be the vertices of the parabola, right? Now, if you set x equals 0 and then try to solve for y, you can already see this particular kind of hyperbola isn't going to cross the y-axis. So you end up with y squared equals negative b squared, or y equals plus or minus square root of negative b squared, which gives us y equals plus or minus I radical b, I here being the square root of negative 1. As you know, this is an imaginary number, so therefore this will not have any real y-intercepts. So that comes with a warning, because you should not jump to the conclusion that hyperbolas never have y-intercepts or never cross the y-axis, because in this particular case they did not, and but I'll show you one in a minute where you may have one or even two y-intercepts. Let's take a look. All right, so notice that with this particular hyperbola, which I have shifted 5 units to the right, meaning the center has shifted 5 units to the right. There's no shifting up or down, so it's just going to be right there, the center. Notice this one would have crossed the y-axis at one point as well, right? So this one would be both an x and a y-intercept, and this one would only be an x-intercept right here at this point. Now, however, notice that if I move it even further to the right, for example, let's say I were to move it 7 units to the right, right? Notice now we end up with actually 2 y-intercepts and also 2 x-intercepts right here. So, so be careful when trying to generalize regarding intercepts as far as hyperbolas are concerned. As it turns out, hyperbolas have 2 asymptotes, as you can see in this image here, which we can actually find the formula for if we do a little bit of algebra. Recall that an asymptote is a line or curve that a graph comes arbitrarily close to but never actually touches or crosses. To find the asymptotes of a hyperbola centered at 0, 0 with a horizontal transverse axis, we start by solving the equation of a hyperbola for y. So here's the equation that we've already discovered. We go ahead and solve this equation for y by starting in this way. We'll go ahead and basically isolate the y squared over b squared term. We end up with y squared over b squared equals x squared over a squared minus 1. So if we do a little bit of algebra before we end up taking square roots, life will become easier. So what we'll do now is we'll go ahead and multiply both sides by pardon me, by b squared, and we end up with y squared equals b squared over a squared x squared minus b squared, right? We're just multiplying both sides by b squared. So we get y squared equals b squared over a squared x squared minus a squared b squared over a squared. We're just combining these two terms. And now if we factor out the b squared over a squared, that leaves us x squared minus a squared. So finally, we take out an x squared as well. Notice that we can factor out an x squared. You may be thinking, but this term doesn't have an x squared in it. But that's fine, because all you have to do once you factor out the x squared is divide each term by x squared to find out what should go in here. So you get 1 minus a squared over x squared. Test it. Go ahead and multiply this in. What do you get? X squared times 1 is x squared. And what's x squared times a squared over x squared? That's going to be a squared. So this is a trick you can use to factor out a particular factor, even if it's not necessarily common to all terms. We don't normally do that, say, in regular algebraic factoring, but sometimes it can be very helpful for us. So here we get y equals plus or minus. We're just applying the square root property. Square root of b squared over a squared x squared times 1 minus a squared over x squared. So y equals plus or minus b over a x times the square root of 1 minus a squared over x squared. This was all a perfect square, so we just brought it out of the radical. Now notice what happens as x approaches infinity or negative infinity. It makes no difference. Basically, this expression here, the a squared over x squared, is going to be just some number over a very large number, so it's going to approach 0. Therefore, 1 minus a squared over x squared is going to approach 1, right? Because you get 1 minus 0, so you get 1, and therefore y itself is going to approach plus or minus b over a x. So this is how we find the two asymptotes for this kind of a hyperbola. And notice those are just basically equations of lines, because it's in the form of mx plus b, where this is going to be the slope, and plus 0, so 0 0 will be the y-intercept of these two lines here that are the asymptotes of this hyperbola. So basically, whenever you have a hyperbola with this equation and this format, meaning a horizontal transverse axis and basically vertices at a and a0 and negative a0, you're going to get asymptotes which the hyperbola is going to become really close to but never touch at plus or minus y equals plus or minus b over ax. Now, because the slope of this line is b over a, that means starting at 0, for example, at 0 0, we can go up b and then right a, right, to get to for example, a point on this particular asymptote, the positive b over ax case, right? So this suggests an interesting thing to us, that if we actually, once we know a and b, if we actually form a rectangle, see, just like that, it's called the fundamental rectangle for this hyperbola, then we can easily draw the asymptotes of the hyperbola through the four corners of that particular rectangle, and then proceed to easily graph our hyperbola by just starting at the the two vertices and then coming closer and closer to those lines from all sides, like so. Okay, so this is the box or the rectangle that makes the graphing of a hyperbola really simple, and it's called the fundamental rectangle. So here's that graph in all its glory and a much larger format so we can see it more easily. So remember, we have a hyperbola with equation x squared over a squared minus y squared over b squared equals 1. We go ahead and form this fundamental rectangle, which are basically very easy. They come from the a and the b in the equation, right? So once we form the fundamental rectangle, we quickly draw our asymptotes, and we go ahead and draw our hyperbola. Very, very easy. And as far as the equation of those asymptotes, one is y equals positive b over ax, the other is y equals negative b over ax. All right, so when it comes to the graph and the formula for hyperbolas with the center at the origin and a vertical transverse axis, they can be obtained in a very similar way, and the results will be as follows. Instead of having x squared over a squared in this case, we're going to have y squared over a squared minus x squared over b squared equals 1. We are still associating the letter a with the transverse axis of this hyperbola and all hyperbolas. However, notice that when we dealt with ellipses, a was always less than b, right? But notice with hyperbolas, a can be less than b, a may be greater than b, or a may even be equal to b. In that case, you'll have like a square as your fundamental rectangle. But here it is. But notice another thing that changes, of course, the slope of this line, instead of being b over a, is going to be up a over b. So it's a over bx, and this one is going to be negative a over b. So the slope for the two lines is going to be a over b and negative a over b, instead of b over a and negative b over a. And their equations will be y equals positive a over bx and y equals negative a over bx. But again, we can create the fundamental rectangle quickly and draw the asymptotes without even really having to find their equations, right? So as far as the graphing is concerned, you only find the equations if you have a reason or have a need to do so. Otherwise, if you just want to graph, all you need is the fundamental rectangle, which you can form quickly using a and b. And basically from a, you draw at a at negative a, you draw a horizontal, and then through b and negative b, you draw these vertical lines, and then you form your rectangle. That's it. And you know that the asymptotes are going to go through the four corners, and then you can graph your hyperbola. All right, so let's see if we can graph this hyperbola and then state the domain, range, center, vertices, foci, and the equation of the asymptotes. Now, remember that hyperbolas of this kind come in two varieties. One where the x squared term is the positive term and the y squared the negative, and then vice versa, right? So when basically the vertices are going to be aligned with the positive case, right? So in this case, because the x squared is the positive term, we know that the vertices are going to fall on the x-axis. Even if this were translated, we would know that it would be kind of a left-right hyperbola rather than a up-down hyperbola. So now all we have to do is go ahead and find the values of a and b to begin with. So remember that because this is where the vertex is, that 144 is going to be a squared, right? So we have a squared equals 144, and b squared equals 25. So this tells me that A is going to be plus or minus 12, and B is going to be plus or minus 5. Now, as far as finding the vertices are concerned, we're ready to go ahead and write that. All we need really is the A values, right, for the two vertices right here and right here, right? So, but we will need the B values when we want to form our what? Form our fundamental rectangle, right? So basically the way you go about doing this, once you find A and B, you go ahead and mark your graph like this, your axes. You put a point at the four corners like that, about not corners necessarily, but those 4 points, right? And then you create your rectangle, then you draw your asymptotes, and you go ahead and graph starting at the vertices, right? Just like that. So the graphing is very easy. Let's go ahead and find the other items that we need. Now, I wanted to quickly backtrack to this page because if you remember, for ellipses, the easy equation to memorize, for me at least, was b squared plus c squared equals a squared. But for hyperbolas, it's actually a squared plus b squared equals c squared. So that's the one that I usually try to memorize and work my way toward the other ones from that point. So we're going to write a squared plus b squared equals c squared. So 144 plus 25 equals c squared. 169 equals c squared. So c is going to be plus or minus square root of 169. Now, if you're familiar enough with numbers, you'll know that's plus or minus 13. So let's go ahead and write some of these facts down. So we know that the vertices are at plus or minus 12, 0. And now we know that the focuses, or the foci, are going to be at plus or minus 13, 0. All right, what about the domain and range for this hyperbola? Well, the domain is basically the set of the x values that can be inputs that generate the points that you see on this graph. So we can see the x values start right at the vertex to the right, and right at this other vertex to the left. So basically negative infinity all the way to negative 12. And you include the negative 12, so you'll want to bracket union, and on this side from 12 onward, right? So bracket 12 to infinity. The range, of course, notice it looks like eventually we'll assume all positive and negative y values, right? Eventually you will reach all positive and negative y values. So the range is going to be negative infinity to infinity. As far as the equations of the asymptotes, these are going to be of the plus or minus b over a x variety, right? So they will be y equals plus or minus 5 over 12x. All right, so there we are. And that's how you basically graph a hyperbola. So again, if you were doing it by hand, you would just go ahead and draw your axes, right? You would locate your 4 main points, the 12, negative 12, 5, negative 5, you would form your rectangle just like that. Then you would go ahead and draw your asymptotes just like that. And these are all dashed because they're not part of the actual hyperbola. They're support objects that help us graph the hyperbola. Then starting at each vertex, you just smoothly move toward each you can see why I pasted this for you, because of the fact that I know myself and I know I'm not the greatest artist. Okay, so but you should definitely do this by hand and know how to do this by hand for your own sake, okay, and your own advancement. Okay, so that is how we handle these hyperbola graphs. And make sure you've answered everything. We've found we've graphed it, found the domain range. The center is, of course, at 0, 0. We have the vertices, we have the foci, and we have the equation of the asymptotes. Okay, so let's go ahead and move on. Of course, after you make sure you can handle this on your own. All right, so this next one we can see is an up-down or vertical hyperbola. Now the y term is the positive one, so we know this is going to be, that's how we know this is going to be an up-down hyperbola. And we know that a squared equals 49 and b squared equals 9. Now, since I'm interested in the length of the A piece, I'm actually just going to say A equals 7 and B equals 3, because I'm really interested in how large that distance is, right? So if I want to deal with distance, I'll just need the positive case, right? Not the negative one as well. But I mean, it doesn't matter if you write plus or minus 7 or not, but just know what you're doing and you'll be fine. All right, so at this point, we can go ahead and find C. We have a squared plus b squared equals c squared, so 49 plus 9 equals c squared, so 58 equals c squared. So C is going to be, if I just want the length of the C piece, meaning the distance from the center to each focus, it's going to be that. So now I can write my vertices. They're going to be at 0 plus or minus 7. I can write the foci. They're going to be at 0 and then plus or minus square root of 58. And the center is obviously at 0, 0. We can go ahead and speak about the domain and the range. The domain is going to be the set of all the x values that are needed to graph this particular object, right? Notice that all x values will have to be in play. So the domain this time is negative infinity to infinity, and the range is what's going to be more limited. The y values that are at play to graph this particular graph are going to be anywhere from 7 and up, or anywhere from negative 7 and down. So let's do the bottom piece first. So negative infinity to negative 7 bracket union bracket 7 to infinity. That's the domain and range. And the only thing we need to find now are the equations of the asymptotes. And of course, remember that they are of the positive, negative a over b x variety, because it's a is here and b is here, so you go up a over b, right? So like that, and you end up with y equals positive or negative 7/3 x. Of course, let's say you sometimes forget this. No big deal. You can just see what the equation is going to be, because it's going to be y equals mx plus b. B is 0, and the slope for this one is what? Up 7/3. The slope for this line is down 7/3. So there you go. Simple. All right, and that's how you graph that one. Next, we want to graph this particular equation. Now, this one is not in standard form, so we're going to go ahead and put it in standard form first. The best thing to remember is the fact that we know, we know this is going to be of the x squared over a squared minus y squared over b squared equals 1 variety, right? Because of where the vertices fall, right? Now, however, and mainly because remember the x squared term is what's so obviously you won't have this graph, but you have the equation, and you know that the x squared term is the positive one, so that's how you know it's going to be a horizontal or right left parabola, right? So but nevertheless we need a 1 on this side, right? So we need to basically go ahead and divide both sides by 51/84. Now on the left side we know it's going to split up, and each one of those is going to get divided by 51/84. So now what we need to do is go ahead and see if 64 goes into that number, because if it does, we can cross cancel and get much simpler numbers, and of course also get the correct format. So let's see, 61/58 divided by 64. Oh no, I put in the wrong number. Hold on, I don't know where I got that number, don't ask. 51/84 divided by 64. That's better. So we know this cross cancel and leave us 81, which of course means 81 goes into 51/84 64 times. And we end up with x squared over 81 minus y squared over 64 equals 1. Notice that because 51/84 divided by 64 is 81, that means 51/84 divided by 81 would be what? Would be 64, right? Okay. So so now the rest is easy, right? Because we know a squared is 81. Therefore, a is, we will go back, switch back and forth. Plus or minus 9. B squared is 64. Therefore, B is positive or negative 8. And notice the correct thing to say is actually positive or negative 8. But a lot of times you say plus or minus 9 or plus or minus 8 because that rolls off the tongue a lot nicer. But otherwise, it's really correct to say positive or negative 8. All right. We can find C because a squared plus b squared equals c squared. So 81 plus 64 equals c squared. So c squared equals 81 plus 64. So 145. So C is positive or negative square root of 145. So we'll try to simplify that if possible. So let's see, 145 divided by 5, that's 29. There's not any perfect square inside the square root of 145. So in other words, if you were to do the prime factorization, it would just look like this. See, on the left side, no perfect square because 29 is prime, right? So so basically we'll leave it like that. All right, now we're ready to say what some of these things are. So we know that because we have the A and the B, we can easily create our fundamental rectangle or box, whatever, and then we can draw the asymptotes, and then starting at the two vertices, we just nicely draw our hyperbola, like so. So as far as the vertices are concerned, we know that they are at plus or minus 9, 0. The foci we know are going to be at plus or minus 1 square root of 145, 0. The center is at 0, 0. And it's a left-right parabola, hyperbola, so therefore the asymptotes will be of the y equals plus or minus b over ax variety. So there'll be y equals plus or minus 8 over 5x. That's it. And those are the equations of the asymptotes. What about the domain and the range? Domain, notice the x values in play to create this graph are going to be all x values from negative infinity up to negative 9, including negative 9, together with, so union, all x values starting at 9 and onward, okay? The range, the set of y values needed to graph this particular equation will be all positive and negative real numbers, right? So in other words, all real numbers. And that's it, okay? That's how you would graph that. Let's go ahead and proceed. All right, next we want to look at the generalized equations for translated hyperbolas in standard form, of course. And it's the usual, we did the exact same thing for ellipses. So this one, of course, would have been shifted to a new center at hk. And the same for this one, the center would be hk. Some of the things change, but notice the length of the transverse axis is still going to be 2a for both cases. The vertices are going to be shifted, of course. Don't panic about having to memorize all this. Once I show you the graph in a minute, you'll see how you can easily find all these without needing to sit there and panic about memorizing a bunch of little ordered pairs like that. The c squared equals a squared plus b squared will still hold, and the asymptotes, of course, are going to be shifted in the same manner. So you take plus or minus b over ax, apply the same transformation. So you're going to move it h units to the right and k units up, right? And depending on the value of h, of course, you may be moving to the left if h is a negative and this ends up being a positive. Okay, so all the same kinds of transformations we've already seen. And as you know, the only thing you need to worry about with these vertical transverse axes is that instead of having b over a, you're going to have a over b for the slope of the asymptotes. Let's go ahead and take a look at a graph of this situation and we'll see what makes sense. Okay, so here we can see a translated hyperbola. Notice that the center is no longer 0, 0, it's at hk. The reason I told you not to panic about memorizing all that is because, look, once you locate the center, in order to get your fundamental rectangle, all you do is from the center go up b units, down b units, right a units, left a units. That's it. You're ready to construct your fundamental rectangle. Then you draw your asymptotes and you proceed to graph your hyperbola, again starting at the two vertices. And that's all there is to it. So it's a really, really simple process. This is, of course, a left-right horizontal one, so you know that it's going to be of this variety, with the x term being the positive one and the y one being the negative one. And for the foci, just remember, from this point, you're going to go c units to the right and c units to the left to get the two foci. And that's all there is to these translated hyperbolas. We'll see some in practice in a minute. And very similarly for these up-down vertical parabolas, again, locate your center. You know, you go up a units, down a units, right b, left b, construct your rectangle, then draw your asymptotes, and go ahead and draw your hyperbola, starting at the vertices, knowing that there is going to be a difference in that, because the y term here is the positive one, you know it's going to be one of these up-down ones. And for the asymptote equations, you also know that it's going to be of the form plus a over b times x minus h plus a k. And there is those, okay? All right, so here we're gonna go ahead and graph this hyperbola and find the required information. Notice that because the x term is the positive one here, this is going to be one of these left-right ones. You know, of course, you won't have the graph to begin with, but that's how you know this is going to be your a here. So a squared is 9. Well, your a squared actually, right? So a is going to be positive or negative 3. Your b squared is going to be 16. So b is going to be positive or negative 4. The value or the distance or the absolute value, of course, is just 3 and 4. And as I mentioned before, this would not happen with an ellipse where a is less than b, but it can happen with a hyperbola, so it doesn't matter here. All right, and we go ahead and we find c. A squared plus b squared equals c squared, so 9 plus 16 equals c squared, so 25 equals c squared, so c is going to be plus or minus square root of 25, so c is going to be plus or minus 5. As far as the absolute value of c, the length that we're interested in, that's going to be 5, right? So now we have the a and b, and we know the center. Center is going to be at, remember, when this is a positive, it's going to be actually at negative 5 And since that's minus 1, you just take the 1. So it's going to be at negative 5, 1, as you can see here. Center at negative 5, 1. So now from there, it's easy, right? To form your rectangle, you go up, how much? 4, right? And sorry, you go up, yeah, that's correct. You go up 4, down 4, and then right 3, left 3. Okay, now remember, you know what this point is here, right? That's negative 5, 1. So what happens when you go up 4 units? Let's say I want to look at what that point is, for instance, right? It's easy because you have to go at the same x value and you add 4 to the y value. So that'll be at like negative 5, 5, for instance. What would this point here be? Same way, right? You go same x value, but you have to subtract 4 from the y value, so you get negative 3. Anyway, do you even need those points? No, I'm just illustrating to you that it's easy to get them even if you wanted them. So because from here you just know you need to go right 3, left 3, up 4, down 4, create your box. Then draw your asymptotes and then draw your hyperbola. Of course, what you need to know is whether it's going to be left, right, or up, down. And you know here, because the x is the positive one, that it's going to be a left, right parabola. Well, I demonstrated that backwards, but you know what I mean. All right. So there's that. We have all that information. Where would now the important, let me erase this so it doesn't clutter up the graph. Oh, I should have left that one. Let me put that back in. So we do need the center. All right, so I need to find the coordinates of the vertices, right? Now, I know that this length here, right, is how much? 3, correct? So now I know that the vertex will be at the same elevation, so the y value doesn't change. But for the x value, I need to move 3 units to the right. So negative 5 plus 3, that gives me what? Negative 2, right? Now for this other vertex, so this is one vertex. For the other vertex, v prime, we know that, again, it'll be at the same elevation, so the y value will be the same. For the x value, we take negative 5 and subtract 3 from it, so we get what? Negative 8. Notice, that's why I was saying you don't need to memorize all that. You just reason it. All right, for the foci. So I know that C is 5, right? So I know that I need to, one focus is going to be at, first of all, the same elevation, so 1, but I need to take the negative 5 and add 5 to it, because remember, C is 5. So negative 5 plus 5, that brings me to 0, which agrees with the graph, doesn't it? Notice the one focus is at 0, 1, okay? For the other focus, F prime, it's going to be at the same elevation as the center and the vertices, so at 1. But for the y value, I need to start at negative 5 and subtract 5 from it, so I get negative 10. And notice that makes sense from our graph. Negative 10, 1 is the other focus. All right, so we have the vertices, we have the foci, we have the center right here. We've graphed it by making our fundamental rectangle, drawing our asymptotes, and then graphing starting at the vertices, right? So we need the equation of the asymptotes. Remember, this is going to be of the y equals plus or minus b over a times x minus h plus k variety. So we're going to have y equals plus or minus b, which is 4, over a, which is 3, times x minus h. Remember, h is negative 5, and k is 1. Okay, so x minus negative 5 becomes plus 5, and then plus k, which is 1, right? So that's going to be the equation of our asymptotes. If you wanted to simplify that, like put it in mx plus b form, etc., you could, but normally those are acceptable. All right. So the only thing left for us to do is to find the domain and range. All right, let's take care of the easy one first. Notice that all real numbers are going to be involved in the y values for these points, right? So the range is negative infinity to infinity. The domain, basically everything from negative infinity up to negative 8. Include the negative 8 union everything starting here at negative 2, so bracket negative 2 comma infinity. That's it. See, I didn't have to worry about all that x minus h plus h and all that. So because you just figure it out, right? Just common sense. All right, and that's how you do those graphs, those translated graphs. All right, so how would you do this one? Notice that when we've had a coefficient like this so far, we've been able to go ahead and divide it off by, or kind of cross-canceling it, because we didn't have a 1 on the other side and we ended up dividing by it and then they simplified. We can't do that here. So what would you recommend? All right, so here's what I recommend. This is what you need to understand. And this is good to know about numbers in general, that if you have a, right, you can write it as 1 over a. Did you know that? All right, in case you didn't, let me show you why. Remember I showed you a trick a while back, which if you have a over b divided by c over d, that's going to end up being this outer product AD, which goes on the top, over this inner product BC on the bottom. And I showed you why that's true, because it's very easy, because you have a over b over c over d, so you get a over b divided by c over d, which becomes a over b times d over c, which is of course what? AD over BC. Okay, so this is a very nice trick to remember. So remember, if I start with 1 over a, I can think of it as 1 over 1 over a, which is going to be the outer product a over 1, which is what? A. Okay, so that tells you that I'm going to erase all that now so we can get on with our actual business. So if I have 16 and I want it to move down to the denominator, I can always write it as 1 over 1/16, like that. So that's how we're going to rewrite that. So we're going to get x plus 5 squared over 1/16, okay? Minus quantity y minus 1 squared over, that's just going to be 1, equals 1. So now we're in standard form. Now, because the x term is the positive 1, we know it's going to be a left-right parabola. That's going to be my a squared. So a squared equals 1 over 16. Therefore, a is going to be positive or negative 1/4. The value I actually need, just 1/4, right? And b squared is 1. So therefore, b is going to be plus or minus 1. And so looking at the equation, I can see the center is at -5, 1, as indicated by our graph here, -5. This is looks like to scale to me as well. So -5, 1. And now that means that point there is -5, 1, right? So for me to get the vertices, right, I need to go 1/4 to the right and 1/4 to the left, right? And in the vertical direction, I need to go B, right? So 1 up, 1 down. And then I can go ahead and form my fundamental rectangle, draw the asymptotes, and then draw my graphs. Okay, you can see this is going to have very high eccentricity from what we discussed last time, right? This particular hyperbola. All right, so that means if I want this vertex, right? Now I know that it's going to be at the same elevation as the center, so the y value is going to be the same, right? But for the x value of the vertex, I'm going to have to take this x value of the center and add 1/4 to it, right? So let's do that down here. -5 plus 1/4, that's -5 over 1. So the LCD is 4, 1 times 4, so -5 times 4 is -20, plus the 1 doesn't change, so -19 over 4. So the x value is going to be -19 over 4. Okay, there's nothing new or difficult on this one. I just wanted you to see that fractions are no different, and I just didn't want you to panic if you see fractions involved. Okay, so for this other vertex, right, v prime, again, we know that it's going to be at the same elevation as the center, so the y value is easy. We'll take care of that. For the x value, we're going to have to take the x value of the center and subtract 1/4 from it, right? So -5 over 1 minus 1 over 4. LCD is 4. So we have to multiply 1 by 4, so we have to multiply the top by 4, so -20 minus 1, so we get -21 over 4. All right, so those are the two vertices. For the foci, for this focus on the right, again, I know that it's going to be at the same elevation at the center, so the y value is 1. The x value, I need to take the x value of the center and add c to it. The problem is we haven't found c first, so let's go find c. That's lowercase c, different from this c which stands for the center. That's a capital C. So we have a squared plus b squared equals c squared. So we know a squared is 1/16, b squared is 1. So we get that. So let's go ahead and combine these two. Common denominator is 16. So the easiest way to do this is just say 16 divided by 16 is 1 times 1 is 1. 16 divided by 1 is 16 times 1 is 16. So we get 17 over 16. That's the c squared. So therefore c is going to be positive or negative square root of 17 over 4, right? I went ahead and took the square root of 16. So for the x value, I need to take the x value of the center and add square root of 17 over 4 to it. Like so. All right, so for this other focus, f prime, same business at the same elevation, so the same y value, but I need to take the x value of x coordinate of the center and subtract square root of 17 over 4 from it, like that. All right, so we have the vertices v and v prime. We have the center at negative 5, 1. We have the foci, and we need the equations of the asymptotes. So we know it's going to be of the y equals plus or minus b over a, because it's a left-right one, times x minus h plus k. So we're going to have y equals plus or minus b, which is 1, over a, which is 1/4, times x minus h. H is negative 5, so x minus negative 5 becomes x plus 5, and then plus k, which is 1. Now, I did say you don't necessarily have to simplify, but if you have something like 1 over 1/4, you should simplify that. You know what 1 over 1/4 is. We've been over this just a minute ago. That's just 4, remember? So you're going to get y equals plus or minus 4 times x plus 5 plus 1. And that's the equation of the asymptotes. Finally, domain and range. Domain is going to be negative infinity all the way up to that point right there on the vertex, so negative 21 over 4. Make sure to include it with a bracket. Union, starting here at this point, which is negative 19 over 4 to infinity. All right. What about the range? That's the easy one, right? Because basically all real numbers are going to be needed as y values. So the range is going to be negative infinity to infinity. And that's it. That's a simple problem. Again, you have to understand the difference between difficult and tedious, right? Tedious means there's a lot of detail, there's a lot of places you can make mistakes. Difficult means actually a tough nut to crack. You have to really figure out what's something that needs to be done. So this is not of that variety. You already know everything you need to do. You've already done it with whole numbers, right? So it's just a little bit more tedious, that's all. Make sure you can handle it, and we'll proceed. All right, next we want to graph this equation. We've seen something similar to this with ellipses, where we found that it was easier to actually go ahead and turn this into an equation of a whole ellipse, and then see whether we need to draw the top part or the bottom part. With this, of course, we're going to try to find the equation of the whole hyperbola, and then choose either the bottom or the top half, depending on the sign here, which is positive. So that means we're going to only be graphing the top half, as you see here, as the end result. But let's see how to get that end result. Okay, so basically what we're going to do is we're going to go ahead and square both sides. All right, so we end up with y squared over 16 equals 1 plus x squared over 100. So if I put it in standard form, it'll be y squared over 16 minus x squared over 100 equals 1. Because the y term is the positive one, I know it's going to be an up-down vertical parabola. So a squared equals 16, so a is going to be plus or minus 4. B squared equals 100, so therefore B is going to be plus or minus 10. We've done a lot of work with equations of asymptotes, etc. Here we're not asked for that, so we don't really need to go there. All we need is to realize this is going to be centered at 0, 0 because h and k are both zeros. So from that center, I'm going to go, because it's a vertical one, I'm going to go up 4, down 4. So I'm going to place points up 4, down 4. And I'm also going to go right 10 and left 10. So now I'm going to go ahead and draw my fundamental rectangle. I do a little bit better on paper and on the actual physical whiteboard, but all right. There you go. I guess it's not the worst. Let me try this part again. All right. Now we're going to go ahead and draw the asymptotes. So everything we would have done to draw the whole hyperbola, we would do. The only difference being that we're not actually drawing the whole hyperbola, right? We're only drawing this particular equation, which is going to be the top part of the parabola. So therefore, we go ahead and draw this as we normally would, moving toward the asymptotes, and we will leave this part off because we're not graphing that part. Remember, we're not graphing this equation. We're graphing this equation. That's why we only want to include the top part. All right, so the only other thing that's asked is the domain and range. Now, domain, notice all x values are going to be needed to graph this graph. All right, so negative infinity to infinity. For the range, only y values starting here and up, right? So it's going to be at 4 and up. So bracket 4 comma infinity. Those are the y values that are at play when it comes to graphing this, which is, by the way, a function, as you can see. If I just multiply both sides by 4, I get y equals 4 square root of 1 plus x squared over 100. I can always replace the y with f of x. So in case you're interested, that's the function that we actually just graphed. And it passes the vertical line test, so it's very much a function. All right, so that's how you do that. Try this one, see if you can come up with the graph that I've shown, and then come back. All right, as you know, we're going to go ahead and square both sides. So we get 25x squared equals, squaring -1 just gives 1, so we just write 1 plus 36y squared. So let's move that to the left side. 25x squared minus 36y squared equals 1. Okay, this is one of those where you notice you have a 1 on the right side already, so that's not going to rescue by trying to avoid the situation here. So here you're going to have to use this trick. Remember, a is the same as 1 over a. So we're going to write it as x squared over 1 over 25 minus y squared over 1 over 36 equals 1. So because it's the x term, which is positive, I know it's going to be one of these left-right parabolas, horizontal parabolas, and so that's going to be a squared, 1 over 25, which gives me a equals plus or minus 1/5. B squared is 1 over 36. Therefore, b is going to be plus or minus 1/6. Okay, so starting at the center, you go 1/5 to the left, 1/5 to the right. It's a very bizarre kind of looking parabola, right? And 1/6 above and below. So it's going to be a tiny box. You could always draw it a little bit off scale to make it a little bit more manageable. Then you draw your asymptotes, right? You know. And you draw your hyperbola. Of course, this is, you know, not exactly beautiful, but you know what I'm talking about. And so the thing to keep in mind is that if I actually solve this for x, I get x equals -1/5 square root of 1 plus 36y squared. So I know that with this left-right parabola, because of that minus, I'm going to be interested in the left part. If we were plus, we would graph the right part of this hyperbola. Okay, so that's all there is to that. What do we do as far as the domain and range? Well, remember where the let me erase all that real quickly. Okay, remember that the vertex here is at -1/5 0. That's going to be important for our domain, right? So the domain is going to be -infinity to that point. The range is, of course, what kind of y values do you need to graph this curve here? All the y values, so -infinity to infinity. All right, so that is that. All right, I've come back to this previous problem we did for a second because it said determine whether the equation can be written as a function. I actually didn't even read that when we were doing it. But yes, we definitely determined it can, and we wrote it. But what about this other one? Notice this one you cannot write as a function because notice it fails the vertical line test. So there's no way you're going to come up with an equation that gives you this curve, which is a function. All right, so that's that. All right, okay, so here's a equation given to you. It's not in standard form, so we're going to put it in standard form like we did with the case of the ellipse, and then the rest is very easy. x squared minus 6x, and I'm going to put the y squared and 6y together, but I'm going to go ahead and factor out that negative first. Don't forget that positive 6y becomes negative 6y once you factor out a negative, right? So what do I need to add to x squared minus 6x to complete the square? Remember, take half of negative 6, which is negative 3, and square that to get positive 9. Okay, you may wonder, why do I write this negative when it's going to get squared and give me 9 anyway? Because in the next step, when you want to do this, when you want to write that part, all you have to do is look here to know that it should be x minus 3 rather than what? X plus 3. Now, what do I need to complete the square here? Well, notice it's the same, so it's going to be a 9 as well, right? However, you got to be really careful. Here, I'm adding 9, right, to get this one. So I need to add 9 to the other side. But on this one, I'm not actually just adding 9. I'm adding negative 9. So I also need to do negative 9 on this side. So I end up with quantity x minus 3 squared plus quantity y minus 3 squared equals what? 16, because that 9 and negative 9 cancel each other out, right? So we need to go ahead and divide both sides by 16 to get our 1 on the other side. This is an example of when I told you A and B may actually end up being equal, right? So this is an example of that kind of a thing. So in order to graph it, you would basically locate the center, which is at 3, 3, right? Then you would go, well, let's see what A is. A squared, it's left, right, so the A is going to be under the X, right? The A squared. So it's going to be under the X part. So we get A squared equals 16. So A is plus or minus 4. B squared is also 16. So B is also plus or minus 4. So this is when I told you that your rectangle may actually be a square. This is one of those cases. So you go from the center, you go up 4. So to 7, and you go down 4 to negative 1. Okay, my graph is becoming a little bit offset. Okay, so let's see, 3 should be there. So 7 and then negative 1. And then you go right 4 from the center again. You go right 4, so to 7, to 7, 3, and left 4 to negative 1. You make your rectangle. Of course, remember, you didn't have to graph this one, but I just want you to know it's not a big deal. My 7 is a little bit off. It's actually here. All right, so you graph that. You're like, why is this guy insisting on graphing when he's so challenged? All right, and then that's the whole point. You got to do what you're weak at so that you improve. All right, so then you do your asymptotes. Now, I'm actually not that bad, again, with a physical paper and a physical pencil or on a whiteboard in a classroom, but it's a little bit difficult on these touch screens. All right, so there you go. Now, the only thing we want the center and the vertices. We know the center is at 3, 3. The vertices are only these two. Remember, those up here and down here, they're not vertices, only these two. So one vertex is at the same elevation as the center, but 4 units to the right. So the center is at 3, 3. So 4 plus 3 is 7. And the other vertex we already saw is going to be at the same elevation. So 3 is the y value, and then 3 minus 4 is -1. So those are the center and the vertices, and that's it. That's all we had to do. We didn't even have to graph it, but I just wanted you to see it's very easy to graph. Okay, that's all there is to it. All right, so give this one a try. You've seen me do one for ellipses. This is very similar. Basically, we're going to put the y term next to each other. 64y squared minus 512y. We'll leave some space because we're going to complete the square, and then write the x terms. And let's go ahead and move that number to the other side. So 13, 16. All right, so let's go ahead and factor out the 64. That leaves us y squared minus 512 is 8. So 8y. I'm going to leave some space and factor out the -36. That leaves me x squared plus 2x. All right. Now we're going to go ahead and complete the square on y squared minus 8y. So take 1/2 of -8, which is -4, and go ahead and square it to get 16. So plus 16. And on the other one, we're going to take 1/2 of 2, which is 1, and then square it to get 1. So plus 1. All right, let's see what we're actually doing, however. Here, I'm not just adding a 16 to the left side of this equation. I'm adding 64 times 16, right? So 1024 is what I'm actually adding, so I need to add that to the other side. I should actually really do that down here. I should have done that in the other problem too, so you know what I was talking about, so it's okay. So because I haven't added it until this point, right? So if I wrote it up here on the previous time that I completed the square, I meant it down here. Here I'm not adding a 1, I'm actually subtracting a 36. So I need to subtract 36 over here as well. Okay? That's all there is to it. So we get 64 times y minus 4 squared minus 36 times quantity x plus 1 squared equals, now we need to do 1316 plus 1024 minus 36, which is 2304. All right, so now we need to go ahead and get a 1 on this side, so we're going to divide both sides by 2304. Splits up on the left side, so each of those is going to get divided by 2304. All right, so we see if 2304 is divisible by 64. Yes, that's nice. So this becomes y minus 4 squared over 36 minus, of course, we know the other one is going to be 64, because if 64 goes into 2304 36 times, that means 36 goes into it 64 times. All right, so the rest is now easy. We can see that the center is going to be at 4, -1, right? 4, -1. And the other way around. See, you got to be careful with this. The x value is here, the h is there. So -1. I'm glad I made that mistake so you could see how easy that is. So -1, 4 is where the center is. The center is always hk. H is always associated with x, and k is always associated with y. Remember that. So -1, 4. And we can see that since it's since the y term is the positive one, this is going to be an up-down parabola, and this is going to be a squared. So a is plus or minus 6. B squared is 64, so b is plus or minus 8. And that's it. So from the center, we need to go up 6, down 6, and then right 8, left 8. But since I really only want the vertices, I'm just going to do the up and down. So the center is at -1, 4. I know that the upper vertex, let's call it V, is going to be at the same x value, but for the y value, I need to add 6 to it. So 4 plus 6 is 10, right? Now for this lower vertex, V prime, I know it'll be at the same x value, -1, but I need to take the y value of the center and subtract 6 from it, so -2. All right, so we have the center, we have the vertices, and we did put it in standard form, okay? And of course, if you wanted to make your box, you would also from this point go 8 to the right, 8 to the left, make your rectangle, draw your asymptotes, and graph your hyperbola. Don't forget, it's going to be an up-down one. That's it. All right, here's one that's a little different. We need to find the standard form of the equation of a hyperbola with x-intercepts at plus or minus 12, 0 and foci at 13, 0. What we need to realize is that this is definitely going to be a left-right parabola. So if it's of this variety, x squared over a squared minus y squared over b squared equals 1. And we need to also notice that a is going to be 12. And c is going to be 13. So we can use the fact that a squared plus b squared equals c squared to find b. So we're going to solve for b squared. We really need b squared because we just want to write the equation, right? So b squared equals c squared minus a squared. So b squared is going to be 13 squared minus a squared, which is 12 squared. So b squared equals 169 minus 144. So b squared equals 25, and b is going to be, well, it's going to be plus or minus 5 or just 5 if I want the length, but I don't even need it because I'm ready to write the equation once I have b squared. So x squared over a squared, which is going to be 12 squared or 144, minus y squared over b squared, which is 25, equals 1. And that's all we need to do. Okay? Here's kind of a similar one. See if you can get this one on your own. You have a hyperbola with vertices at 0 plus or minus 12, so it's an up-down vertical one, and asymptotes with this equation right here, plus or minus 4x. All right, so because it's up-down, that means it's going to be of the variety y squared over a squared minus x squared over b squared equals 1, right? Now, we know a is going to be 12. So therefore, a squared is going to be 144. And we don't know b or c, but we know this is the equation of the asymptotes. We know what that coefficient should be. Remember, it's up-down, so it's going to be of the variety y equals plus or minus a over b x, right? So that means a over b must be what? Must be 4. So we know what a is. A is 12. So 12 over b equals 4 over 1. Cross multiply, so we get 4b equals 12. So b equals 3, which means b squared is 9, right? Now we're ready to write the equation. So y squared over over a squared, actually. A is what? A is 144. So a squared is 144. So 144 minus x squared over b squared. So that'll be x squared over 9 equals 1. That's it. Okay? Make sure you understand that, and we'll move on. All right, here's an interesting one. See if you can figure it out before you continue. All right, so we want an equation of a hyperbola with vertices at plus or minus 2, 0, which tells us what a is. Because it's left-right, it's going to be of the x squared over a squared minus y squared over b squared equals 1 variety. So a is 2, so therefore a squared equals 4. Now, that's basically all we're given and 1 point on the hyperbola. So we know we have x squared over 4 minus y squared over b squared equals 1. But we know a point on the hyperbola, 4, 1. So I'm going to substitute 4 for x. So I get 4 squared over 4 minus, I know y is 1 at that point, so 1 squared, which is 1 over b squared equals 1. Now I need to solve this for b. Let me simplify this first. That's going to be 16 over 4, which is 4. So I have 4 minus 1 over b squared equals 1. I'm going to go ahead and multiply both sides by b squared to clear the fractions. Don't forget to distribute on that left side. So we end up with, these cancel out. So we get 4b squared minus 1 equals b squared. So 4b squared minus 1, well, minus b squared equals 1, right? Let's move the b squared to the left side and the negative 1 to the right side. So we get 3b squared equals 1. So therefore b squared equals 1/3. So we have x squared over 4 minus y squared over 1/3 which is b squared that we just found, is equal to 1, right? So x squared over 4. Now remember, 1 over 1/3 is what? 3. So I can write minus 3y squared equals 1. There is the equation that we were looking for. And if you really want to clear all fractions, you could do that too. Multiply both sides by 4. You would get x squared minus 12y squared equals 4. You really want to make it in standard form, move everything to the left side. General form. So there's the general form. That up there right here is the standard form. This is some mid-range form, but it's kind of a nice form on its own. All right, so that's how you do that one. All right, so here we want to write an equation for a hyperbola that has vertices at 3, 9, and 3, -1, and asymptotes with these equations. Now, remember that if we figure out what this distance between these two vertices is, this distance from here to here, right? Then we can take half of it, and that'll be our A, right? Now, notice from elevation 9 to elevation -1, that's a total of 10. So that means our A is going to be 5. And we know that this equation here is of the form y equals plus or minus a over b times x minus h plus k. So the slope here is a over b. So that means a over b equals 7. I know what a is. A is 5. So 5 over b equals 7. So 7b equals 5. So b equals 5 over 7. And I'm pretty much ready to write the equation, right? Because I know this, the h is going to be 3 from right here. K is 4. So I'm going to have x. Well, actually, it's an up-down one. So actually, y minus k, which is 4 squared over a squared. So that's going to be 5 squared, which is 25. Minus quantity x minus h, which is 3 squared over b squared, so 5/7 squared, that's b squared is going to be 25 over 49. All right, so one useful trick, another useful trick. If you have 1 over a over b, what is that? That's b over a. Why? Because 1 over a over b, outer over near, so it's b over a, right? So equals 1. So we get quantity y minus 4 squared over 25 minus, well, if they wanted it in standard form, you would have stopped right there. But since we like to get it out of this form, if possible, we'll go ahead and flip that. So we get 49 times quantity x minus 3 squared over 25 equals 1. That looks a little nicer, right? But this is standard form right here. And if you multiply both sides by 25 and move the 1 onto the left and go ahead and square those, you can get the general form. All right, that's all we have to do for that one. All right, the last thing we want to do today is talk about the eccentricity of a hyperbola, which we've already spoken about a little bit in the last video. Here we'll go ahead and calculate a couple of eccentricities, and that will be it for today. So recall that the eccentricity of a conic is a measure of how much a conic section deviates from being circular. Also recall that the equation for finding eccentricity is given by this equation, E equals c over a, where we have c being the distance from the center to either focus and a being the distance from the center to either vertex. Now we know for a hyperbola, we've been doing this all day, c is just going to be the square root of a squared plus b squared, right? Because remember, a squared plus b squared equals c squared, so c is just going to be the square root of a squared plus b squared, right? We're interested in the positive value of c. So also, because clearly this square root is going to be more than a, because obviously the square root of a squared itself is a, so here you're adding some positive number to that, so that's definitely going to be greater than a. So we get that c over a is going to be some number larger than a divided by a, which is going to be what? Greater than 1, right? So therefore, e is going to be greater than 1 for all hyperbolas, right? Let's go ahead and actually calculate a couple, and then we'll call it the day. All right, so here's our equation. X squared over 3 minus y squared over 15 equals 1. So we have a squared equals 3, b squared equals 15. We know that eccentricity is c over a, which is going to be the square root of a squared plus b squared over a. So we're going to have the square root of 3 plus 15 all over a, which is of course going to be, if a squared is 3, that means a is going to be the square root of 3. So over the square root of 3, right? So notice that's going to be the square root of 18 over the square root of 3. Since they're both positive, we can go ahead and do this, right? So we get square root of 6. So to get a feel for that, we'll go ahead and compute it. So we get approximately, where did you go? 2.4, which is quite high, as you know. So this deviates quite a bit from the being circular. If we look at it on a graph, you'll see why. All right, as you can see here, it's quite an elongated hyperbola, and that's why you can see the eccentricity was so large. All right, here's the last problem we're going to do today. See if you can figure it out and then come back and check with me. Find the equation of the hyperbola with eccentricity 2 and foci at -9, 5 and -3, 5. So we have E, which is the same as C over A, is equal to 2, right? Now we know the foci are at -3, 5. So I'm not even going to graph a Cartesian coordinate plane. I don't need to. It's going to be at -3, 5, and I know it at the same elevation, so somewhere to the right at actually the other way around. So the -9 goes there, -3 goes here, right? Because remember, -3 is larger than -9. So this is the scenario with the foci, right? And we know that the center is going to fall exactly halfway between the foci, right? So if we need the midpoint, remember the midpoint formula for 2 points is going to be x1 plus x2 over 2, comma, y1 plus y2 over 2. This is from quite a bit earlier in the semester, but that means the center here is going to be at basically the average of -9 and -3, that's -12 over 2, so -6. And of course 5 plus 5 over 2 is just 5. So there's the center, which means that's H and that's K. Now we know that this distance from here to here is what we refer to as C, And how much is that? Well, negative 6 plus what gives you negative 3? Plus 3, right? So that's going to be our C, right? So if I plug in for C over here, I get 3 over A equals 2. So that implies 2A equals 3, which implies A equals 3 halves. So now I have A and I have C. I should be able to find B, right? Because, or B squared anyway, that's what I need. First of all, realize that A squared is going to be 9 over 4. Now I know that A squared plus B squared equals C squared for hyperbolas. So B squared is going to be C squared minus A squared. Now C is 3, so we get B squared equals 3 squared, or 9 minus A squared, which is 9 over 4. Now if I simplify that, I get 9 times 4 is 36, minus 9. 9 from 16 is 7, so 27 over 4. So we have enough information to write our equation, because we have, we know it's a left-right hyperbola, so it's going to be of the x minus h squared over a squared minus quantity y minus k squared over b squared equals 1. So we have x minus negative 6, which becomes x plus 6 squared over a squared. A is 3 halves, so a squared is 9/4, minus y minus k, which is 5, over b squared, which we found to be 27 over 4, equals 1. Now if we want to get it out of this fraction in the denominator kind of situation, we can just go ahead and move the denominators up, right, using the technique that we know. Remember, 1 over a over b is b over a. So we get 4 times quantity x plus 6 squared over 9 minus 4 times quantity y minus 5 squared over 27 equals 1. And that is how we would find an equation of such a hyperbola. All right, and with that, I think you've had plenty for one day. I'm sorry it became a little bit long, but such is life, right? Okay, so you take care until the next video.